The second one is more interesting and more challenging as well, right? Let's kill this guy. Watch a poll for the second. This is second. So this is crank me challenge, but it's not executing in your local setting. If you connect to the socket, there's a corresponding program is running behind the scene in my server side, and then you get this same thing. In fact, you can exploit this one exactly same as your local environment. But here, what we are not gonna have, unlike the local environment, although we kind of provide a binary and libc, but you cannot just work in the same offset within your computer because the libc in the server side might be different from yours. So very good idea to synchronize two environments with the technique that I'm going to show you today, right? So if you go to the server, we have the binary that we collected for you. For example, tutorial in remote. These are the target is running behind this socket, right? This one is the actual binary that you're interacting. So we first gonna copy this target sec ccom, and then we're gonna exploit this one in my local setting. But at the same time, you can kind of know the exact environment behind the scene. For example, if you type LDD, and these are the library that is going to be used with this program, and this is the loader that will load this program as well. So in order to synchronize this setting with ours, we're first going to copy this same binary and library within my local environment, right? So let's copy. So let's first copy the libc from the server to here. And then let's copy the loader. Here. So I also copy the target binary as well. If you run the target.ccom, in fact, you are not actually running the target.ccom. In fact, the loader that is written as part of this binary format will take care of this loading process. So we're going to do the exact same things in my local environment. This loader can be run. So we copy this corresponding binary, like libc and loader and target.ccom. In fact, if you just run the target.ccom, most likely you can actually run, right? But if you attach the GDB, your mapping of those libc, in fact, they're actually using libc in my setting, right? Our job is to replace this libc with the libc that server is using, so that when you're writing exploit, everything is synchronized, right? As you can see in the libc is from my system directory, right? First, I'm gonna show you how to replace them. And we're also using the dynamic linkers in my local setting, right? But in fact, you can easily change that with this technique. In fact, you can just invoke the loader. You can run the loader. Loader is actually an executable one. In fact, you can launch the loader with the binary. But unfortunately, it couldn't find the corresponding version associated with this linker. In this case, we can change the path of the library so that the loader, dynamic linker, can find the corresponding libc for you. So this is another trick. You can say load library path, and you can specify corresponding path that linker is looking for in terms of library. In this case, libc exists in my current directory. I just provide the dot here, right? If you run this, now everything is running. And if you attach GDB, this is a program. If you see the mapping, see the libc under my current directory. So they are not using the libc in my systems, but they're using libc in my current directory, which is the same as a server right now. And also, we're using the dynamic linker from the current directory instead of dynamic linkers in my systems, right? So if you write the exploit against this particular setting, you will get all this payload and address will be correct. So that when you're exploiting through this whatever socket that we provide, you will get the exact setting, right? It's a good idea to do all the program it's a good idea to write. Do I have this? Okay. Let's write the exploit against that. In fact, this target sequence is not, in fact, the exact same binary that you've been working on. I think, so if you provide long input, let's check. I think it's the exact same length, 40. So after 40, we can control the instruction pointer, right? So battery. But here, instead of just invoking the target.ccom, we're gonna invoke loader first. Where is it? Yeah, we're gonna invoke this setting, right? And target ccom. And then we're gonna set the involvement variable so that we can load the libc library within my current setting, right? So we can launch the process. And see if we can crash. Cannot open the library path. See if we can run, right? So we now process is running behind the scene with the exact setting that we work. See if we can crash them. It crashed as expected. That brief, right? Now you have exact same execution involvement. Unlike previous week, we manually formulate all this return-oriented programming gadget, but we're gonna utilize a tool that Pwntools provide. make your life way easier, right? One of the trick here, I can show you in Python console. And there is a module called ELF. So if you specify corresponding binary as part of the ELF, you can easily interact with so that you don't have to hard code anything. For example, let me show you how it works. If you load this target.ccom, in fact, you can access to any GOT table in this way, or PLT, so that in fact you don't have to look around all these details by yourself. Or sometimes you can even get the libc and many other information directly through these ELF objects, right? Or you can also have access to all the symbols. For example, if you want the address of a star, you can get in this way as well. So we're gonna leverage this one when you're writing exploitations. So another trick that we're gonna also talk about again is a return-oriented program utility provided by the Pwntools as well. Not surprisingly, its name is ROP, but it accepts the ELF objects because we just load the ELF of my target. If you can provide the ELF to this ROP, and it searches through all these gadgets so that it makes your life much easier in terms of writing exploitations. For example, I don't know what is a good things to invoke. Exit. So basically, if you just programmatically just provide this what you want to do as part of this ROP chain, it formulates all this chain for you. Your job you can actually debug, you can actually provide this raw input by yourself as well. Not sure you can invoke if you provide chain. In fact, this is how you invoke the exit by using this ROP based on the ELF. You don't have to look around the corresponding pop gadget by yourself because it can find it for you. In fact, you can invoke any GOT or PLT exposed symbols as well. In this case, our first job is to list those code points. In this case, we're going to leverage this ROP chain so that you can invoke the put as a result, right? So here, first invoke the exit and put, right? Or if you want to create, let's create ROP again. We like to fill some of the buffers right before we launch the ROP chain. In this case, we have to fill about 40 so that we can provide about 40 worth of the raw input. And then you can invoke a put, right? This is what we want to do. And GOT of the put as input, right? So that we like to dump the GOT of the put through the put call. And then, right? If you invoke the chain, you will see this of the chain that you have to provide. Or if you like, you can actually dump and debug as well. In this case, I didn't set properly the context is they consider this is a 32-bit architectures, but in fact you can also change that. For example, 64. Let's do it again. ROP ELF. We're gonna fill about 40, and then we're gonna invoke the put with the argument of GOT to the put, so that when we execute this ROP chain, we can get the code pointer of the put, right? And then if you dump, you can see this is a ROP chain formulated based on the ELF context. For example, it fills about 40 worth of dummy value and jump to the pop RDIM return, which you can set the first argument. Again, as you can expect it, the first argument is the GOT of the put, and then it put the return address as a put, so that when this ROP chain is executed, the put will print it out the GOT of the put, which likely the code pointer that you can find in libc, right? It's pretty easy, right? So we're gonna use the exact same ROP chain techniques in this context as well. Say we first have to set the context properly, so that when they are formulating the ROP chain, they know what type of architectures that we are working on. And let's do this. So I just load the ELF, and we're gonna create the ROP chain through this ELF. We're gonna first provide about 40 worth of dummy value, and we're gonna do the put in the GOT of the put in this way. And then similar to what we did before, we're gonna do we're gonna prepare for the second ROP chain, but for the time being, let's crash the program, right? In this case, just provide the depif. Just for debugging purpose, I dumped the ROP chain, and for actual payload, you can invoke the ROP.chain. Okay. Oops. So as you can see here, something is printed. Likely it's address of the put in libc. See, 7F, and starting with this, right? Another technique that we're gonna do, in fact, similar to the ELF. In fact, you can load the ELF by yourself as well, and you can create the ROP chain. For example, libc. We have a libc in my local directory, right? We just copy from the server, and through this, you can also create the ROP chain by yourself. But at the same time, instead of searching through all these symbols, you can actually access the addressed symbols in this way, right? In this case, I look up the symbols named put, so then I have address, starting from the address 0. Right? So this is the offset of the put. One way to verify this, whether this is correct or not, the address of the put ended with 70, which is nicely matched with the symbols in libc in my context, right? So here we're gonna load the libc. We first gonna read back the output of the put and calculate. So we're gonna read until maybe here, invalid password. And then we're gonna read until here, so that because we're gonna return back from main. Here, instead of crashing the program, let's jump back to start, right? First, because after we invoke the put with the GOT, I read back and see if I correctly read the older value before I decode this one. I launch the program, and what's the output? This is the output. It seems to be correctly read all the value, because again, we know that the 70 is the the least significant bytes of the puts in terms of offset, and we can eliminate this value to get the corresponding put address, right? You can do the similar trick that we did. Ignore about 5 bytes, 1, 2, 3, 4, 5, and just to and then you can decode. We now have an address of the put. How to calculate the libc base? libc provides these symbols of the put and subtract the put. No, the other way. Starting from put, and we extract the offset of the put so that you get the libc base, right? And then for the debugging purpose, so we got this one, right? See if we can correctly get the libc base by executing them. No attribute of ljust. It's not slice. So it seems we got the corresponding libc base. How to verify? The least significant byte is nicely page aligned, or similar to what we did before, target. In fact, you can connect to the GDB. So this is my GDB. Oh, or you can, in the proc, you can access all this information self-mapping. This is libc. See, this is the base address of the libc. So it's nicely mapped. So in fact, we got the libc base of the target binary, and our job is to formulate another ROP chain, right? So pretty easy. So everything is just wrap around. You can smash the stack once more, and we're gonna do another ROP chain. But in this case, we are not gonna utilize the libc of we're not gonna utilize the ROP chain of ELF, but we're gonna utilize the ROP chain of the libc. Right? Similar to what we did before we go for the ROP chain of the libc, because we already got the base address of libc, you can inform the libc module of the ELF so that when they're formulating the gadget, they can correctly calculate all these address for you as well. In this case, you can specify address of the libc base that we have. Starting from here, again, we're gonna get the ROP chain. First, similar to what we did, we're gonna skip about 40 bytes, and then what do you like to do? What are the 3 system goals we like to invoke? The open, read, and write. When it comes to open, what are you going to open first? We like to have the proc flag. Unfortunately, we don't have any proc flag in this setting right now. So for the time being, let's play with this because it's local environment, right? Let's first play with this local setting. Similar to what we did in the Crank Me challenge before, let's search it through the SH. Okay. How do we get the SH? In fact, this one also provides a bunch of interesting tools. Here with the libc, you can search, literally search, bin shell, but it actually return a iterator so that you can just invoke the next, or in Python, this is the libc bin shell string that exists in the program, in the libc, right? So this is what we're gonna do. Let's copy this guy. Bin shell. first open bin shell, and the second argument would be read only, open, read. Once we read, the whatever the proc flag is read in the program, they're gonna assign the next file descriptor into your process. In this case, it's 3. And what is the second argument? The buffer. But we don't know anything about the buffer, right? But fortunately, this binary itself is not PIE enabled, so that you can just pick any value, right? Dump the map. What's a read-writable section? This sounds a read-writable section. Plus about half. Let's pick this one as our buffer that we're gonna play with, right? Let's copy this one. This is a buffer that we're gonna load entire bin shell and write to file descriptor output. So in this case, probably dump the entire bin shell. So because we're gonna create the symbolic link, ignore the bin shell, and we're gonna create the symbolic to the shell, right? Print ROP dump. Right? It sounds right. Let's try. This is a ROP chain. Seems right. They didn't print it out. Stop the program. Oh. First, we didn't create the. Oh, we have a shell. Proc flag. Here's the libc base. Push. ROP chain. Open. Read. Right. Okay. Sounds right. Free bin shell. So one good way to debug, you can attach GDB here and see if we actually proceed as expected. Attach, process. So here we like to stop right before taking the return address that we smash. In this case, return, right? Set the breakpoint here. So right before we sending the ROP chain, we stop. We stop and attach the GDB and send the ROP chain. Hopefully stop there and see they properly executed, right? Launch everything. GDB should be attached. A little bit larger. So it seems we are posing at the right place. If you can see here, properly chain through the gadget, the first argument, second argument, and then open, right? Let's proceed. Oops. Let me execute one more time. We make this a little bit larger. This window is too bad. I wanted to show you in parallel. Let's move this guy other place. Okay, here, go to the next one. Next one. We are taking this, we are setting the RDI register, as you can see in the pop. Second, and take the return. Now about to open. Here you can check the register whether we are opening to the right way. So what is RSI? Hopefully, 0. RDI, RSI. So basically we are opening the SH correctly, right? Finish the execution and see if it's correctly returned. Yeah, correctly return the file descriptor from the open call. Yeah, proc flag is open. We are executing the second gadget, pop, right? And read. See if we are properly providing all the gadget after this pop gadget. We're about to execute the read. Check the register. RDI, RSI, buffer. Sounds alright. This one, why this one is not executed? Readable. See, there was mistakes. So this value, I think 0 is dropped. This, right? We are providing buffer that is not readable. That's why I crash. Right? Kill this guy. GDB. See? Now our chain is working, which is good. Now is the time to set for the remote setting. So everything is working in this local, but unfortunately we are using SH, which you cannot have control in the remote setting. If you just run this one, in fact, the system will looking for the SH in their local environment. So we need to create this proc flag string. The previous technique that we did in previous setting is copying around, right? In fact, you can do many other things here. One technique is just to read one more time from the user so that you can construct the buffer. Again, previously we copy around this string to make those one, but now let's just copy them, right? Let's just get the input from the user because we have the read. So before we open, we're gonna do read from the user input. We're gonna store to the buffer how many string? Say flag worth of string. Proc flag. So we're gonna read proc flag length of the string to the buffer, and then we're gonna read buffer because we read those proc flag, we store this proc flag to the buffer which is empty, and we're gonna use the same buffer to open, and we're gonna use the same buffer to read and write, right? So in order to do this, delete this guy. Right after sending the chain, we have to send flag, right? So that when chain is executed, they're waiting for the user input. In this case, we provide the flag as part of this read system calls, and then we can execute the ROP chain will be executed accordingly, right? So let's delete this shell, see if it's working. Not working. Did I set flag? Buffer. Let's attach the GDB. Let's do the debugging. So the plan here is to see if this read is working properly after. Let's see, everything is just working as expected. Seems right. Where is it? Let's launch the GDB. Here, the first gadget. Oh, second gadget. Where is open? Oh, read from the user's input. Okay. And we are executing the gadget starting from return to here. And we are executing the read. Let's first check the user input. We're gonna read this amount. RDS. Why it has something inside. Okay, this is a buffer that we like to accept user's input, right? Interestingly, it has something. Interesting. Finish the execution. It's waiting for user's input, right? And let's provide some. Oops, where is it? So we provide the user input. Check the buffer. Is that the buffer? Seems buffer is not correctly aligned. Okay. So we got some string inside. Right? See if we can inject proc flag. It seems there we need some pause here. And because after we send the ROP chain, there is a chance that they accept everything together. So that we need to either break or fill the buffers, whatever you want, or pause a little bit. It's not a good idea to pause it here, like with the OS time and whatnot. You better understand the source code and how many bytes they're actually accepting. And then you can fill the buffer so that we can pass along. But like when here, let's put some time. I think probably that's the reason. Just 1 second, stop. Proc flag. Because I checked this one contain user's inputs, right? So that we can see. Otherwise, we have to debug one more time. So working with debugging remote environment is very annoying, frankly. See, it works after just this weird timing, right? It sometimes works, sometimes doesn't work. But my guess right now is that whenever you send the two things at the same time, because the buffer effects in your socket, the input is not divided well enough. So that after sending this one, we wait until the ROP chain is executed, and then at the moment you can send this one. Okay. Now we properly send the proc flag to the buffer and read everything without any dependencies in my local setting, right? Let's perform the exploit. So instead of opening the process here, in fact, you can just do remote. What's the port number? You should remember. This is a port number, right? Hopefully it work. Yeah, you get the flag, right? That's all for today. Feel free to ask questions. We highly recommend to complete your tutorial. There are a lot of things you have to do the debugging, for sure, right? Thank you, everyone.